Alright, welcome back. Now we're on to part 2 of our lecture about, we're still in the part of the chapter there that's about turbine-to-turbine wakes. This idea that an upstream turbine creates a wake in the flow that has certain properties, like it's turbulent, it's slower than the flow around it, it is expanding horizontally and vertically, downwind, etc. Let's model them. Let's come up with a way of describing what these things are doing. Now, deriving these things are not so important. Rather, let's actually think about what these equations mean. And your book spends most of its time on the so-called N-O-Jensen model. By the way, it is N-O-Jensen, not No-Jensen, which the book does not make clear. N-O-Jensen is a noted wind power engineering specialist. He's, I was going to say he's an old dead white guy of science, but I believe he's alive. N-O, I think he's Niels Otto or something. He's Danish. And he developed this model that describes what the wind speeds in the wake should be. He's got this number UW of x, that is the wind speed inside the wake at a distance x downwind from the turbine itself. This is fundamentally what you're trying to solve for. Okay, this is the quantity that we want to know. What is the wind speed x meters downwind from the turbine itself? And unsurprisingly, it depends on the value of UI, the environmental wind speed broadly in the area of the turbine itself, the flow that did not go through the turbine. And it's got a couple of these other parameters in there, like d, the diameter of the rotor itself, which probably makes some measure of sense as to why that would be in an equation that describes how a wake is working. It's got this strange number ct. Ct is the so-called thrust coefficient. And this is a fairly technical, jargony kind of thing from engineering about how a turbine actually works. It's hard to see how a turbine has thrust. You might think of it as being kind of like the opposite of a fan. I mean, you can see how a fan has thrust. Well, think of a turbine as sort of a fan that just works the other way around. So there is this property of the blades and the pitch and things like that called the thrust coefficient, and you are certainly welcome to investigate on page 137 to learn more about thrust coefficient and how it's computed and so on. I'm not planning on making a big deal about that. It's in general a given in a problem. And there's also another parameter here in this N-O-Jensen model called K. K is a broader idea in like local flow and so on. It's called a wake decay constant. In the context of a wind turbine, it's a constant that that describes how the wake will be shaped and so on. And in the context of a wind turbine, they give you this relatively simple definition of the wake decay constant here, where h is the height of the hub of the turbine itself, and z is the aerodynamic roughness length of the surface around the wake that the wake is moving over, like grassland or whatever. And it's just a simple thing you compute, okay? K can be defined lots of different ways in different contexts for different kinds of turbines and so on. This is a good catch-all for like common applications like HOTS. Forward-facing HOTS over a smooth surface, this is lovely. This will be just fine. And using this relatively simple definition of, oh, well, that's a horrible looking equation there, but okay, it doesn't, I can't really envision what this thing's going to look like, but we should be able to do an exercise. And so your book just throws exercise 7.1 at us. Let's actually look. In exercise 7.1, let's say we have a 100-meter tall turbine with 50-meter long blades, and we're going to just be given that the thrust coefficient is 0.7. It's going to be a number from 0 to 1. And we're just going to give you 0.7, okay? Let's not worry about how it got computed. The roughness of the area, the aerodynamic roughness length will be 3 centimeters. That happens to correspond to grassy surfaces. And the wind upstream, that UI, is going to be 10 meters per second. Now, what the problem asks you to do is to draw a graph of then what the wind speed inside the wake is going to be from a distance of 2d to 5d, where d, remember, is the diameter of the rotor. So let's see, if d is going to be, well, if the radius is 50, d is 100, so we're going from 200 to 500 meters downwind. Okay, well, I can think of a number of different ways to solve a problem like that, but I'm kind of a spreadsheet guy. I like to use spreadsheets for certain kinds of problems, and so let's just do a couple, let me just show you how I did this problem here. Alright, so I took a little Excel spreadsheet here, And I made myself a little table at the top that just gives me all the information that were givens in the problem. I have H and R and D and CT and ZO and UI and all this blah blah blah. And I actually computed K right there. And you can see when I make an Excel spreadsheet, I like to actually go ahead and put the units in the next column and actually a little bit of text to remind me what each of those things are in the fourth column and so on. But this is just the pattern of how I do it. I just thought I'd kind of show you how I solve a problem like this. Okay? Then, in order to actually solve this, we're going to be making a graph. In Excel, the way you make a graph is you make two columns of numbers, where one will be the X value, associated with the ordinate on the axis, and the other column will be like the Y or the abscissa on your axis. And so I made a column of numbers that go from 200 to 400, because we're supposed to be plotting this from 2 rotor diameters to 5 rotor diameters down. Okay. I did not sit there and type 200, 201, 202, 203. I used fill, but you may or may not know how to do better, smarter ways of doing it than that. And then I actually entered the formula. In fact, you can actually see the formula that I entered there in the formula bar in Excel. It's kind of that big fat box in there in the middle of the screen there. You can see it's UI times 1 minus square root of blah, blah, blah. And you can see I actually did a number of fancy Excel tricks there, like used named ranges and stuff like that. But I did that just so that the equation looks a little more logical than, cell names in Excel, A2 and B4 and all this kind of stuff. Alright, so I actually made my my little plot there. My 2 columns, and then I just in Excel told it to plot column 1 as the x-axis and column 2 as a y, and I get this diagram right here. Which is, as your textbook helpfully mentions, is not the most exciting looking graph in the world. It's a line. It is not quite a line. I mean, if I got my ruler out or something, I could see that it does have some curve to it, but it's basically a line. And I can see how at 200 meters out the wind speeds are low, and at like 500 meters out the wind speeds are high. Boy, that's a big, oh wait, look at my y-axis. They're only going from, the y-axis only runs from 7 to 8.5 meters per second. Let's actually normalize this axis a little bit and have it run from an origin at 0, 0 up to 10. Oh, well, now I can see my wind speed is actually only changing a little bit over that distance from 200 meters downwind to 500 meters downwind. Now remember, UI, our wind speed, that was the environmental wind speed, the initial wind speed, the wind speed that was not, of air parcels that did not go through the turbine, was only 10 meters per second. So at 200 meters downwind from the turbine, we had a wind speed right around 7 meters per second. And then 500 meters downwind, we had a wind speed of about 8.1 or something like that. Even 500 meters downwind, 5 rotor diameters downwind, our wind speed UW is not, inside the wake, is nowhere near our initial wind speed of 10 meters per second. I'm also amazed in this particular problem, by the way, the efficiency of this turbine is not all that great. It's just how this particular problem was set up with that value of the thrust coefficient. But you might remember, for example, the most efficient turbines, this is from our Betz's law lecture, the most efficient turbines would be making it so that the wind speed downwind was 1/3 of the wind speed upwind. That was in fact how you get the most efficient turbine. And in fact, that would mean that the wind speed downwind would be 1/3 of the wind speed upwind, or about 3.3 meters per second. And you can see we haven't extracted anywhere near that much wind power here. But then again, most turbines are nowhere near as efficient as Betz's law would allow them anyway. So, alright. Realistically, this particular graph only ran out to 500 meters or 5 rotor diameters. Let's actually see what the Jensen model would tell us about going farther downwind. So I computed the same model, just did the extent, all I literally did is just copy and pasted my cells down farther on the Excel spreadsheet until I got out to like 1.5 kilometers, 1.6, something like that. And, extended my diagram out, and now I can see that as we get farther and farther downwind, the wind speed inside the wake is increasing, getting actually pretty close to the environmental wind speed of UI by about, 1.5 kilometers downwind. By then we're, about 15 rotor diameters. By 15 rotor diameters out there, we're at, the wind speed's about 9.6 meters per second inside the rotor, about 10 meters per second outside the rotor. Wind speeds vary second by second, even fraction by second, fraction by second. Realistically, we're well within the measurement error at this point. Okay, realistically, by about 10 rotor diameters downwind, it's getting really hard to find. If you actually had an anemometer out there, you'd have a hard time finding the wake by about 10 rotor diameters downwind. Enno Jensen's model actually tells us more interesting things too, plus our broader theory about what that constant K is all about. It actually tells us things about like how wide horizontally our wake should be. The width of our wake should be equal to d plus 2kx. So, like for example, at x equals 0, the location of the turbine itself, then if you do the math there, oh, the width of the turbine's wake should be d, which is the width of the turbines themselves. That makes sense, right? The turbine, the wake is the same size as the turbine itself, the blades, the rotor itself. And then as we go downwind, you'll see that the wake's width increases linearly downstream. This is just a linear function of x, right? K is a constant in here, so it's just something times x. It's just a linear equation. Okay, that makes sense. Alright, now before we go and take this Enno Jensen model and compare it to a second model, let's answer 3 or 4 quick questions. Question 5. Without doing any math, just take a look at this term here. We can look at the equation for the Enno Jensen model and realize that that term that's in the square brackets is going to have to be A, negative, B, positive but less than 1, or C, positive but greater than 1. Look at this equation here and think through what does this have, mathematically what has to be the case of that term that's in square brackets. Make a choice from those 3 options and get a little feedback before you move on to question 6.